In the first part of this video lecture, we gave motivations for pi systems and lambda systems, stated a theorem about uniqueness of measures, a very general theorem. Then we stated that the coincidence class is a lambda system, and also that we use the uniqueness theorem to prove that the Lebesgue measure is indeed unique, as promised already in the previous video lecture. In the second part, we moved to the pi lambda theorem, which we will state without proof. We'll just accept this theorem as being valid and true. And then we use this theorem to prove that uniqueness theorem indeed holds. And before that, we'll first prove that the coincidence class is a lambda system as stated in the first part of this video lecture. Recall what our motivation was. We were trying to study the class of sets for which the measure mu and nu are the same, and we stated that it is a lambda system. We had discussed that lambda systems, they have some structure, but they are not yet the same level of structure as being a sigma algebra. What they miss is exactly the requirement that they are closed under intersection, which are pi systems. And here we see somewhat magically that requiring the coincidence class to contain a smaller class that generates all the sigma algebra, we can prove that the measures coincide on the entire sigma algebra. And this is exactly provided by the pi lambda theorem. And here is the statement of the theorem, and it is exactly what allows us to get from two classes that have different types of structures to say that we can boost that to taking a sigma algebra generated by the smaller and usually simpler of these classes. So what the theorem says is, if a pi system is contained in a lambda system, then the sigma algebra generated by that pi system is also contained in the lambda system, which we can think backwards is, if a lambda system contains a pi system, then it also contains the sigma algebra generated by that pi system. Now let's complete this picture by showing how this can be used to prove uniqueness. So recall we're trying to prove this theorem. It has certain assumptions. The assumption is that the class of sets for which the measure mu and nu coincide, it contains a class C which is closed under intersections, and there is also this technical assumption that we'll address later, and it ends by concluding that the class in fact contains all the sigma algebra generated by C. So here we are defining this class formally. That's the class of sets that have same measure mu and nu. And by the previous proposition, and here it is, the previous proposition, this class is a lambda system under a certain assumption, which is exactly the same assumption that we are making here. Now, we can conclude from the pi lambda theorem that this class D, since it contains a class C which is a pi system, it also contains the entire sigma algebra generated by that pi system. And that means exactly that the measure mu and the measure nu of sets A and the sigma algebra generated by this class are the same, and this is exactly what this theorem was saying. But of course, this was assuming that beforehand we knew the measure mu and nu were the same and they were finite. That's a big assumption. We want to drop that assumption now. And if we go back here to what is the theorem we are trying to prove, it has an assumption that will allow us to overcome the lack of that assumption, which is we can find a class we can find a sequence of sets which are in this class, they increase to the entire space, and they have finite measure. And this is the assumption that I'm replicating here. This is exactly what is assumed in the theorem. And then how do we move forward? Well, we define restricted measures. This is the very slick part of the argument. We have this sequence. They are in the class C. They increase to omega. So we're going to do the following. For each n, define a measure which is finite, and where mu and nu also they coincide on these sets by assumption. Then we're going to define this restricted measure that assigns to every set just the measure of the overlap of that set with this term an in this sequence. So we're defining a sequence of measures mu n and nu n. And now we note that for each a in the sigma algebra generated by C, we can take, we know that mu n of a equals nu n of a. Here, we know that these terms are equal because we are back to the first case here. And if they're equal for every n, when we take the limit over n, they're still equal. But now, on the other hand, we have this equality here, meaning this limit equals this measure, simply because if we take these sets indexed by n, this is a increasing sequence of sets, and it increases to a. And here we're just using the fact that mu is a measure, and measures have this property of continuity from below. And this will conclude the proof. We're just missing one piece in this story, which is we have not yet proved this proposition that the class, the coincidence class, the class of sets for which the two measures mu and nu coincide, they form a lambda system. And let's prove that now. What does it mean, first of all, to be a lambda system? There are three requirements. The first one, the entire sample space has to be a member of the class. The class has to be closed under complement, and it has to be closed under countable disjoint unions. Well, the first requirement is already provided by the assumption of the proposition, so there is nothing to check. But now we can consider the second requirement, being closed under intersection. Being closed under complement, How do we show that it's closed under complement? Well, take some set in this class. Okay, what does it mean for the set to be in this class? It means the measure mu and the measure nu are the same on that set. Then, well, what is the measure of the complement of A? This is simply the measure of omega minus the measure of A. We can write it this way because we are assuming this measure is finite. And since mu and nu of omega are the same, we can replace this. And since we are assuming A is in the class, we can also say that nu of A equals nu of A. So this is the same as the nu of A complement, which means A complement is in the class. So we checked the second property already. And now we want to check the third property, which is being closed under countable disjoint union. So take a sequence of sets in this class D, which are disjoint, and we want to show that their union is also in the class. Well, now here we just use first the assumption that each member of the sequence is in the class, so these measures are the same. If they're the same, then of course their sum is the same. So this checks this equality. And for this equality here, we just use the fact that mu is a measure. Measures are sigma additive, so the measure of a disjoint countable union is the sum of the measures. And we use the same to show equality here. So in the end, mu of this union equal nu of this union, which means the union is in the class, and this concludes the proof.